G'day. Imagine you're trying to land a helicopter, not on a helipad or even a moving ship. Imagine trying to land it on a single tiny cork bobbing in the middle of the Pacific Ocean. Now imagine that cork is also spinning unpredictably, and it's millions of kilometers away. And you're controlling the helicopter with a time delay of several minutes. This sounds impossible, right? Well, this is surprisingly close to the challenge that space agencies face when they try to land a spacecraft on an asteroid or a comet. It is one of the most audacious, complex, and delicate maneuvers humanity has ever attempted in the vast emptiness of space. We've become quite good at space exploration. We've sent rovers to Mars and probes to the outer reaches of our solar system. We have landed humans on the moon, a celestial body with gravity we can work with. But asteroids are a completely different beast. These are not grand, spherical worlds with a powerful gravitational pull to guide you in. They are small, often potato-shaped remnants from the birth of our solar system. Their gravity is thousands, sometimes hundreds of thousands of times weaker than Earth's. Getting close to one is a cosmic dance of precision. Trying to touch it is like trying to catch a whisper. The slightest nudge can send your multi-million-dollar probe tumbling away, lost forever. A gentle push, which would be nothing on Earth, becomes a powerful shove in the near-zero gravity environment of an asteroid. The surface you're aiming for might not be solid rock, but a loose pile of rubble, a cosmic dust bunny held together by forces we are only just beginning to understand. It's a realm where our earthly intuitions about physics completely fail us. Every action has an exaggerated and often unexpected reaction, making the simple act of landing a nail-biting, high-stakes gamble against the strange laws of the cosmos. You might be wondering, with all this difficulty, why even try? Why spend billions of dollars and decades of work to touch a floating rock that might only be a few hundred meters across? It seems like an immense amount of effort for a very small target. Surely there are bigger, more impressive destinations out there for us to explore. The answer, it turns out, is that these small rocks hold some of the biggest secrets in the entire solar system. These asteroids and comets are not just rocks, they are time capsules. They are pristine leftovers from the very dawn of our solar system, over 4.5 billion years ago. On Earth, gravity is a constant, reassuring presence. It is the invisible force that holds us to the ground, keeps the oceans in their basins, and pulls a dropped apple firmly to the floor. We live our entire lives under its influence, and our intuition is built around its unwavering rules. But when you travel to an asteroid, all of that earthly intuition becomes dangerously misleading. These are tiny bodies, mere pebbles on a cosmic scale. An asteroid like Bennu, the target of NASA's OSIRIS-REx mission, has a gravitational pull that is about 100,000 times weaker than Earth's. This isn't just a small difference, it's a fundamental shift in the rules of the physical world. On a body like this, the very concept of down becomes tenuous. So what is this force that becomes so feeble on these small worlds? Gravity is a fundamental property of matter. Anything that has mass, from a single atom to a giant star, exerts a gravitational pull on everything else. Earth is massive, nearly 6 trillion kilograms, so its gravity is strong, creating a deep gravity well that is hard to climb out of. Take the asteroid 433 Eros, which was visited by the near Shoemaker probe. It has a mass of about 6 trillion kilograms. That sounds like a lot, but it is 1 trillion times less massive than Earth. Its gravity is so weak that if you stood on its surface, you would weigh about the same as a piece of paper. The strangeness of low gravity doesn't just affect the spacecraft. It defines the very nature of the asteroid itself. On Earth, gravity is a powerful sculptor. It pulls everything down, compacting sediment into rock and holding mountains together against the forces of erosion. Our world is solid because gravity crushes it into shape. But on an asteroid, where gravity is just a whisper, things are different. Many asteroids are not solid chunks of rock at all. Instead, they are what scientists call rubble piles, loose collections of boulders, gravel, and dust, held together by their own incredibly weak mutual gravity and maybe even other more subtle forces. Imagine a bag of sand in space. It doesn't collapse into a solid ball, it just floats as a loose cloud. So you've navigated the treacherous orbital dance and you're finally ready to touch down. Your spacecraft is moving at a snail's pace, just a few centimeters per second, towards the surface. On Earth, This would be the gentlest of landings. But on an asteroid, where gravity is barely a suggestion, this is where one of the biggest challenges begins: the bounce. Because there's so little gravity to hold the spacecraft down, the moment it makes contact, it's almost guaranteed to rebound. The European Space Agency's Philae lander, part of the Rosetta mission, experienced this firsthand in 2014. It was designed to fire harpoons into Comet 67P the moment it touched down, anchoring it to the surface. But the harpoons failed to fire. Philae hit the surface just as planned, but then it bounced. It traveled a full kilometer back up into the comet's weak gravity field, staying airborne for nearly 2 hours before coming down again. Even if you could solve the problem of bouncing, another terrifying challenge awaits you. Don't really know what you're landing on. From orbit, mission planners use high-resolution cameras to map the surface and pick a landing spot that looks safe, flat, smooth, and free of large boulders. But flat and smooth are relative terms. What looks like a gentle plane from a few kilometers up can reveal itself to be a treacherous landscape upon final approach. The OSIRIS-REx mission at asteroid Bennu encountered this exact problem. Initial observations from Earth suggested Bennu would have large, sandy, beach-like areas, perfect for collecting a sample. But when the spacecraft arrived, it found a world covered almost entirely in rugged, boulder-strewn terrain. The final landing site, nicknamed Nightingale, was a tiny crater only a few meters across, surrounded by what they called mountain-sized boulders. On Earth, dust is, well, just a minor annoyance. You wipe it off a shelf, and that's that. But in the vacuum of space and on the surface of a low-gravity asteroid, dust becomes a formidable and pervasive enemy. Asteroid and comet surfaces are covered in this layer of fine-grained material called regolith. When a spacecraft touches down or even just fires its thrusters nearby, this dust gets kicked up. But because there's no atmosphere to create swirling dust clouds, and very little gravity to pull it back down quickly, the dust behaves in very strange ways. It can actually form a persistent static charged sheet that hangs around the spacecraft for hours or even days. This levitating dust poses a serious threat to the mission. They can get into sensitive mechanisms, jamming moving parts like robotic arms or solar panel deployment systems. They can cover camera lenses, blinding the spacecraft's scientific instruments and navigation cameras. The story of humanity's quest to touch an asteroid actually begins with a mission that wasn't even designed to land. In the late 1990s, NASA's Near-Earth Asteroid Rendezvous, or near Shoemaker, spacecraft was sent to orbit the oddly shaped asteroid 433 Eros. Its primary goal was to study the asteroid from a safe distance, mapping its surface, analyzing its composition, and giving us our first extended close-up look at one of these ancient bodies. But as its mission wound down and the spacecraft ran low on fuel, the mission team decided to try something audacious. They decided to attempt a landing. This was a high-stakes gamble. The Near Shoemaker probe had no landing gear, no harpoons, no systems designed for contact. The plan was to use its remaining fuel to perform a series of braking maneuvers, slowing its descent to a crawl. On the 12th of February, 2001, mission controllers held their breath as they sent the final commands. It snapped pictures furiously as the ground rushed up to meet it, revealing rocks and dust with unprecedented clarity. But something incredible happened. The signal didn't die. Against all odds, Near Shoemaker had survived its landing, gently touching down on the dusty surface of the asteroid. Japan's space agency, JAXA, took the challenge head-on with a series of incredibly ambitious missions. The first, named Hayabusa, which is Japanese for peregrine falcon, launched in 2003 with a bold objective to land on the small potato-shaped asteroid Itokawa, collect a sample of its surface, and bring it back to Earth. This had never been attempted before. The mission was plagued with challenges from the start, including a massive solar flare that damaged its solar panels. When it finally reached Itokawa in 2005, it found a world that was not a solid rock, but a loose pile of rubble, making the landing even more dangerous than anyone had anticipated. The landing attempt itself was a dramatic, nerve-wracking affair. Hayabusa was designed to briefly touch down, fire a small projectile to kick up dust, and collect the resulting debris in a sample horn. Despite the immense struggles, Hayabusa's return capsule blazed through Earth's atmosphere in 2010, a fiery testament to the team's perseverance. Building on this hard-won success, JAXA launched Hayabusa 2 in 2014, targeting a different type of asteroid named Ryugu. This mission was a masterpiece of execution. It successfully performed 2 touchdowns, collecting samples from both the surface and the subsurface after creating an artificial crater with an explosive impactor. Not only did it collect its samples flawlessly, but it also deployed multiple small rovers onto the asteroid's surface, which hopped around in the low gravity, providing mobile viewpoints. While some missions targeted rocky asteroids, the European Space Agency set its sights on an even more enigmatic and challenging target, a comet. Comets are, well, dirty snowballs of ice dust and rock that spew gas and debris as they get close to the sun. The Rosetta mission, launched in 2004, spent a decade chasing Comet 67P Churyumov-Gerasimenko through the solar system. Its goal was to not just fly by, but to enter into orbit around the comet and deploy a small lander named Philae onto its surface. They chose a site named Agonising, and in November 2014, the world watched as Philae was released. The descent took 7 agonizing hours, with the lander slowly falling towards the comet's nucleus. The plan was for Philae to fire 2 harpoons into the surface upon touchdown, anchoring it against the bounce, while a thruster on top would fire to push it down. But as Philae made contact, the harpoons failed to deploy, and the downward thruster also failed to fire. Without anything to hold it down, the lander bounced. This first bounce was enormous. In the comet's minuscule gravity, Philae flew for nearly 2 hours, traveling a full kilometer across the surface before touching down a second time. It then bounced again, for a shorter duration, before finally coming to rest on its side, wedged in a dark crevice beneath a cliff, far from its intended, sunlit landing site. NASA's next major foray into the world of asteroid sampling was the OSIRIS-REx mission, a name that stands for Origins, Spectral Interpretation, Resource Identification, Security Regolith Explorer. Its destination was Bennu, a small carbonaceous rubble pile asteroid. The primary goal was similar to Hayabusa 2's, to collect a pristine sample and return it to Earth. However, the method was different. Instead of a quick touchdown, OSIRIS-REx was designed to perform what the team called a touch-and-go, or tag maneuver. When OSIRIS-REx arrived at Bennu in 2018, it sent back a shockwave through the scientific community. The asteroid wasn't the smooth, sandy world they had hoped for. It was a chaotic mess of boulders, a celestial landmine with almost no safe places to touch down. The team spent nearly 2 years meticulously mapping every square meter of the surface, creating one of the most detailed planetary maps ever made. In October 2020, the spacecraft began its fully autonomous 4.5-hour descent. The moment of contact was astonishing. The sample head didn't just touch the surface, it plunged nearly 0.5 meter into it. The surface responded not like solid rock, but like a fluid, a pit of loose gravel and dust. So, how do you solve a problem like the cosmic bounce? If gravity won't hold you down, you have to bring your own anchor. This has led engineers to design some incredibly aggressive and clever solutions that seem more at home in a whaling vessel than on a sophisticated spacecraft. One of the most dramatic ideas is the use of harpoons. The European Space Agency's Philae lander was equipped with 2 of them, designed to fire explosively into the surface of Comet 67P the instant its feet made contact. Another variation on this theme is the use of microspines. Imagine a landing foot covered in tiny sharp hooks like the claws of an insect. As the lander touches down, these spines would dig into the porous, uneven surface, providing hundreds of small anchor points to grip the asteroid and resist the tendency to bounce off into space. For even more security, some designs have proposed using drills or screws. Much like putting a screw into a wall to hang a picture, a lander could have drills integrated into its landing feet. While harpoons and anchors are all about holding on tight, there's actually another approach, and that's to use a feather-light touch, actively counteracting the bounce with really precisely controlled forces. This is where thrusters come in. A spacecraft is already covered in small rocket engines or thrusters, which are used for navigating through space. As the lander makes contact with the surface, it could fire a small thruster located on top of the spacecraft, pointing upwards. That would create a gentle, continuous downward push, effectively creating artificial gravity for a few critical moments to keep the lander pressed against the surface and damp out any rebound. NASA's OSIRIS-REx mission used a variation of this thruster technique, not for landing, but for its touch-and-go sample collection. The entire maneuver was a ballet of thruster firings. The spacecraft descended under the control of its thrusters, touched the surface, and then the same thrusters fired again to push it safely away from the asteroid. This precision control allowed it to make contact at a specific location with incredible accuracy, and then depart immediately before it could lose its balance or get stuck. Perhaps the most important tool for landing on an asteroid isn't a piece of hardware at all. It's not a harpoon or a thruster, it's the software. It is the sophisticated, autonomous brain of the spacecraft. Because of the immense distances involved, there is a significant time delay in communications between the spacecraft and Earth. For OSIRIS-REx at Bennu, this delay was more than 15 minutes each way. This makes real-time human control impossible. The spacecraft must be able to land itself from the final approach to the touchdown all on its own. To do this, engineers developed remarkable autonomous navigation systems. A leading example is natural feature tracking used by the OSIRIS-REx mission. As the spacecraft descended, its cameras took rapid-fire pictures of the surface below. The onboard computer then compared these images in real time to a detailed three-dimensional map of the asteroid that had been preloaded into its memory. By recognizing specific boulders and craters, the natural features, it could pinpoint its exact location and velocity with incredible accuracy. This autonomous brain also has to be smart enough to know when to give up. Alongside the navigation maps, engineers also load a hazard map, which identifies all the dangerous areas to avoid: large rocks, steep slopes, or deep shadows. During its descent, if the spacecraft's navigation system determines that it is heading towards one of these hazards and can't correct its course in time, it has the authority to abort the landing attempt entirely. So, we've explored the mind-bending physics of low gravity, the hair-raising challenges of the bounce, the unpredictable surfaces, and the ingenious tools we've invented to overcome them all. We've followed the dramatic stories of missions that dared to touch these distant worlds. It's an incredible amount of effort, risk, and expense. But what is the ultimate payoff? Why does it matter so much to grab a few handfuls of dust from a cosmic rock? It's because these asteroids are not just rocks. They are time capsules. They are the cosmic Rosetta stones that can help us decipher the very origins of our solar system, and maybe even ourselves. Planets like Earth are constantly changing. They have atmospheres, weather, volcanic activity, and plate tectonics that churn and recycle their surfaces over millions of years. This process is called differentiation, and it has effectively erased the evidence of our planet's earliest history. But asteroids and comets are different. They are the leftover building materials, the scraps and rubble that were never incorporated into a full-sized planet. By landing on them and bringing back pristine samples, we get to study the raw ingredients that built our entire planetary neighborhood. Analysis of the samples from asteroid Ryugu has already revealed the presence of uracil, one of the 4 essential building blocks of RNA, a cousin to DNA. Beyond unlocking the secrets of our past, there is another, much more immediate and pragmatic reason why landing on asteroids matters: planetary defense. The story of life on Earth is punctuated by catastrophic impacts from space. The most famous of these, of course, is the asteroid that wiped out the dinosaurs 66 million years ago. But that was just one of many. We live in a cosmic shooting gallery, and while the odds of a major impact in our lifetime are low, the consequences would be devastating. Understanding the threat is the first and most critical step in being able to do something about it. Visiting these near-Earth asteroids, landing on them, and even taking samples is the ultimate reconnaissance mission. It allows us to understand what these potential threats are actually made of. Are we dealing with a solid, dense chunk of iron, or a loosely packed pile of gravel and dust held together by faint gravity? This information is absolutely vital. If we ever discover an asteroid on a collision course with Earth, our strategy for deflecting it would depend entirely on its composition. A solid body might be nudged with a kinetic impactor, basically hitting it with a spacecraft, as NASA's DART mission successfully demonstrated. But trying to hit a rubble pile asteroid with a high-speed projectile might not work. Instead of pushing it, you might simply shatter it into many smaller pieces, potentially making the problem even worse by creating a shotgun blast of impacts instead of just one. Our journey to touch the smallest worlds in our solar system is really just beginning. The incredible successes of missions like Hayabusa 2 and OSIRIS-REx have opened a new frontier in space exploration. They have transformed asteroids from distant points of light into tangible places, worlds with their own unique landscapes, bizarre physics, and profound secrets. We have proven that we can navigate the vast distances, dance with the ghostly gravity, and overcome the immense technical hurdles to bring pieces of these ancient bodies back to our laboratories. The future of this exploration is even more exciting. Upcoming missions plan to push the boundaries even further. The European Space Agency's Hera mission, for example, will visit the Didymos-Dimorphos asteroid system to study the aftermath of NASA's DART impact. Other proposed missions aim to visit metallic asteroids, thought to be the exposed iron cores of shattered protoplanets, which could offer insights into the formation of planetary cores like Earth's own. Beyond pure science, these missions are laying the groundwork for a future where asteroids could become a vital resource. These rocks are rich in valuable materials, from precious metals like platinum to simple water ice. Water is especially valuable in space, as it can be broken down into hydrogen and oxygen to create breathable air and rocket fuel. So, we come back to that initial image, landing a helicopter on a spinning cork in the middle of the ocean from millions of kilometers away. It still sounds almost impossible, yet we have done it. We have landed on bodies with gravity so weak it is barely a whisper, surfaces as fragile as a pile of dust, and have brought back treasures that are rewriting the story of our own existence. The quest to land on these distant rocks is more than just a technical challenge. It is a profound expression of our curiosity as a species. It is driven by the same impulse that led our ancestors to cross oceans and explore continents. These missions remind us that our solar system is not just a collection of 8 planets. It is a vast, complex, and dynamic place, filled with billions of smaller objects that each have a story to tell. By visiting them, we learn not only about the birth of planets and the origins of life, but also about the delicate and sometimes dangerous nature of our own cosmic home. The knowledge we gain helps us protect our future from impacts while simultaneously giving us a deeper and more humble appreciation for our own small, fragile world in the vastness of space. It's a journey of discovery and self-preservation, intertwined. The science is extraordinary, the engineering is ingenious, but perhaps the greatest value of these missions is in their power to inspire. They show us what we are capable of when we work together to pursue a difficult and ambitious goal. Ultimately, the quest to land on a speck of dust is worth it because these specks are not insignificant. They are the building blocks of worlds. They are the messengers from a time long past. They are the guardians of the secrets of our own origins and the potential keys to our future survival and expansion into the cosmos. To touch one is to connect with the deepest history of our solar system, and in that gentle, carefully orchestrated touch, we learn a little more about the universe and a great deal more about ourselves.